Good morning, children. In Unit 3rd, Magnetic Effects of Current, in the last lecture we have done Ampere circuit law, and now the next topic is solenoid. This is the application of Ampere circuit law. Now what is a solenoid here? It is an insulating long wire closely wound in the form of a helix such that its length is very large as compared to its diameter. Now you can see this is the example of a solenoid in which here whenever insulating wire is wounded over a cylinder and when the cylinder is removed, then we get a shape like this. This is a helical shape. Now we can say that when the current is passing through a conductor, then magnetic field is produced around the conductor. Now here you can see that the magnetic field in a solenoid, it is given like this, that this is the direction of magnetic field line, and the magnetic field is such that it is given by the bar magnet. Suppose this is a north pole and this is a south pole. So we can say here that this is a starting point, this is the end point. From here it is starting and it is come to end at this point. So we can say that whenever the magnetic field is produced in a solenoid, then it behaves as a bar magnet. Now you can see that inside the solenoid the magnetic field lines are parallel. If the magnetic field lines are parallel, then the total magnetic field is given by the vector sum of all this magnetic field. So inside the solenoid the magnetic field is uniform and it is maximum. Outside the solenoid, due to repulsion, now due to repulsion, the magnetic field lines, they cancel their effect. So outside the solenoid the magnetic field is very weak, or you can say that outside the solenoid the magnetic field will be zero. But inside the solenoid the magnetic field is uniform and it is maximum. So whenever we do the derivation for the solenoid, then we will take that magnetic field inside the solenoid is uniform and maximum, but outside the solenoid the magnetic field is very weak and it is considered as zero. Now we have a next topic, that magnetic field intensity due to solenoid. Let us take the Amperian structure such that this point shows that magnetic field is produced from this point, and this point shows that magnetic field will come to end at this point. Now this is PQRS. The length of PQ is L, and this is the direction of magnetic field here. Let capital N is total number of turns, L is length of solenoid. So we can write here small n, capital N upon L. Therefore we can write capital N is N into L. Now according to Ampere circuit law, we can write here B vector dot dl vector, that is equals to, this is mu naught capital N into I. We can put the value of capital N, this is NL into I. Equation number first. Now the total magnetic flux through this structure PQ, QR, Rn and Sp. Here this is a small length dl. Direction of length element is same as the direction of magnetic field. For this QR, direction of length element dl is perpendicular to the direction of magnetic field. For Rs, it is outside the solenoid. I told you earlier that outside the solenoid magnetic field is 0, so B will be 0. For SP, direction of length element dl is perpendicular to the direction of magnetic field. So now we can write here total magnetic flux B dot dl, that is equals to B dot dl along PQ plus B dot dl along QR plus B dot dl along RS, B dot dl along SP. Now we can write here for the PQ, direction of dl and magnetic field is same. So we can write here for the PQ B into dl cos 0. For the QR we can write here B into dl cos 90. For the RS magnetic field is 0. So for the RS 0 dot dl, for the SP we can write here B into dl cos 90. Cos 90 is 0. This product is 0. Cos 90 is 0. Cos 0 is 1. So only we get here B into dl. If we integrate dl, then we get total length L. So B dot dl is equal to B into L, equation number 2nd. Now from first and second, we can write mu naught n L into I B into L. So we get B is equal to mu naught n into I. This is the required expression for the magnetic field due to a current carrying solenoid.